Okay, guys, good to see you again. Let's keep talking. I've got this interesting problem from Dr. Deborah KATZ's book pertaining to physics. We call it the KATZ book, the one we're using for the calculus treatment, for mechanics calculus treatment here. KATZ Volume 1, First Edition, Chapter 14, Problem number 57. The problem is essentially telling us this. There are two rods, two solid rods. One's copper, one's steel, and they're welded together, put together, however you want to put it. They're put together in such a way that they're not going to come apart when they're pulled, for our purposes. There's a force F vector going that way. There's a force equal to F vector in magnitude, but going in the opposite direction that way. So a force F going in that direction and a force F going in that direction is pulling this combination of the two metallic rods. The two metallic rods are together, so they're not going to come apart. They've been soldered together, welded together, somehow put together. They're not going to come apart, and they're being pulled this way. This one's steel, this one's copper, this one's length 1.4 meters, this one's length L. The force F, the magnitude of the force F going to the right is equal to the magnitude of the force F going to the left, and that magnitude force is 6 times 10 to the 4th newtons. The length of the copper rod is 1.4 meters, like we said. The length of the steel rod is not known, but we're trying to find out what the length of the steel rod is. The cross-sectional area of the cylindrical shape copper rod, the cross-sectional area is 2 square centimeters. The cross-sectional area of the steel rod, also of cylindrical shape, is 1 square centimeter. So cross-sectional area of copper, 2 square centimeters. Cross-sectional area of steel, 1 square centimeter. One's twice as big as the other, so there's some mathematical, in terms of area, some mathematics we can do here. Young's modulus of steel is 2.0 times 10 to the 11th pascals. Young's modulus for copper is substantially smaller, relatively speaking, and it's 1.1 times 10 to the 11th pascals. 10 to the 11th pascals in both instances, but this one's nearly twice as big as the other. So Y of steel, 2.0 times 10 to the 11th pascals. Y of copper is 1.1 times 10 to the 11th pascals. A stress is equal to an elastic modulus times a strain. It looks a lot like force equals Kx. The force is the stress. The force is analogous to the stress. So when they do something like this, it's a lot like when they say, let's have a look here, how do you do it? Stress, elastic modulus, that'd be the Y, and this would be the strain, and that looks a lot like F equals Kx. The epsilon is associated with length or proportion of length. The amount of length per original length. The amount of length of elongation in this case, the amount of length of elongation, so to speak, in this case, or it could be contraction as well, but for our purpose we're not doing that. The amount of length of elongation delta L compared to the original length L. Delta L over L is epsilon. That is equal to the strain. The stress is force divided by area. The force that is being exerted over a cross-sectional area. So the stress is force exerted over a cross-sectional area. Force exerted over a cross-sectional area is stress. And delta L over L is the strain. Y is Young's modulus. It's a constant. A stress is equal to the amount of stress that's occurring in this situation, force over area, is equal to a constant times the strain. Strain has elements of length associated with it because strain has elements of length associated with it because strain is delta L over L, and stress has elements of force associated with it because stress is force divided by area. And Y is the constant, much like K is the constant. So there's elements of length to be spoken of. there's elements of force to be spoken of, and there's a constant. Epsilon is delta L over L, whereas X is just delta L. Y and K are constants. Sigma is F over A, and F is just F. So here's F over A. Here's a constant, here's a constant. Here's delta L over L, and here's just delta L. So the equations that describe what are going on here, much of what describes what is going on here, much of the physics that goes on here can be modeled in some way, shape, or form according to springs. The equation associated with springs and the equation associated with solids that are experiencing a deformation due to a compression or to an elongation that's taking place, they look very similar what's going on here. So that's what they're trying to say here, guys. So you can see a lot of this. And again, you just can't help. That looks a lot like F, that looks a lot like K, that looks a lot like S. Looks a lot like F, looks a lot like K, looks a lot like X. Sorry. And that's it. And there's a lot of similarities there when we say this. Young's modulus, not surprisingly, would be F over A divided by delta L over L. I guess that would make sense because just like where to go here, guys? Force equals Kx. K is in terms of force divided by a distance. Let's say, force divided by distance is what K is associated with. That's a distance right here, and here's force. Well, with stress equals Young's modulus times the strain, this is F over A. It looks a lot like this. Here's an F. The other one's an F over A. And here's this, and there's a constant right here. Here's a constant again. And this is delta L over L. Well, I guess you could see there, if that's the way they're going to do it, looking similar to this, you guys, you got F over A equals something of the form F over A divided by delta L over L. Times delta L over L. Well, this guy looks a lot like X, this looks a lot like a K, and this looks a lot like an F. And the K right here, well, the K is really F over D right here. Their version of the K, the Y, is got kind of their version of a force and their version of a distance. A force, a distance. Something similar to a force, something similar to a distance. It's got force in it at least. Notice when you cancel these out, it'll all come out there. So again, you just can't help but see it, as we have said. Forgive me, guys. Stress equals Young's modulus times the strain. And here are the analogies that we talk about. So there's a lot going on. A lot of the mathematics, very similar mathematics, operates here as does here. And you can use springs to do a lot of things, actually. You can mimic a lot of what goes on with springs. Okay. Well, with that in mind, what are they trying to say here? Well, they're saying there's an elongation here. If they're asking here if both of them stretch a particular amount. So what we got here is, let's see exactly where we want to go. At the end of all this, you guys, you know, the delta of the copper is going to be the same as the delta of the steel when the force is applied. It's like saying delta L1 equals delta L2 equals delta L. They both stretch delta L. There's going to be this force, a force here of 6 times 10 to the 4th newtons, a force here equal to 6 times 10 to the 4th newtons, and a force here also equal to 6 times 10 to the 4th newtons. Both bars are going to elongate the same amount. And that's what I'm saying here. That's what we're saying here when we look at this. So this one I think is worth keeping here. So on and so forth. So, if that's the case, guys, it's some pretty straightforward mathematics. We know that there's not going to be a rupture here of the bond that is here. There's not going to be a rupture here from this bond. It stays, which means there's a pull this way and there's a pull that way. There's the same amount of pull. So, and nobody's broken. I mean, they just both stretch. This guy stretches. The copper stretches delta L. The steel stretches delta L. This doesn't get pulled apart. So the pull here and the pull here at this point is the same as F vector here. And on this side, F vector, F vector. F this way, F that way, this way, that way. They're pulling. There's an this amount F vector pull that way and F vector pull that way. Okay, there's a lot going on here. Basically, this guy's getting stretched. F vector that way. Simple as that. Getting pulled by this guy that way. And so this guy this way, this guy that way. And this guy's getting pulled by him that way and that way. So it's F vector, F vector, F vector, and F vector. Okay, so a lot going on here, but it's very much a lot of the same stuff going on when you're doing it. So, I mean, there it is. Well, we wrote it. I guess the question they're asking, the big question here, guys, at the end of the day here, they're asking for that answer. What's the length L got to be for delta L to be the same for this guy as it is for that guy? It's as simple as that. Number of ways to go. Here's the data. At the interface, we talk about there's a tug of war. There's all kinds of tug of wars going on. In fact, at the interface, again, like I said, there's a pull this way, there's a pull that way. There's F vector. There's a lot going on here. You could also say F vector pulling this way, F vector pulling that way, and that's kind of where we're going. If F vector equals F vector, there's an equation there, guys. Simple as that. So let's see what we can do. Let's see here. So we got KATZ's book here. We already said it. We talked about the volumes. You got all this, you guys. We have this. I don't like to erase any of it, to be honest with you, but let's erase a few things and go from there. Well, okay, there's so many ways you can argue it, and it almost comes across contradictory, but with all the equality of forces that are taking place here, guys, equations are to be found And that's what we want. We want to get an equation here. At the interface, so at the interface, guys, that implies F vector here, F there. And that's at the interface. Okay? So, all right, we've seen a lot of the mathematics. That's huge. We know what's what. Let's just do it now. Let's apply what we've known and gone over related to that. So erasing some of these. You have it. You have access to it in the book. And you'll have access to it in the film. You can always go back. I always seem to forget. I think I'm in a live lecture sometimes, guys, so I do a little more repetition than I would like to do otherwise. But let's see what we got here. I mean, we got this, and what the heck does that mean? Well, you know, force equals force, as we said, guys. So let's try to think of a good way to say this. I'll argue with myself here a little bit on this whole process. Is it true that, well, let me be a little more rigorous. Let me not jump the gun quite as quickly. We've already said this. We've already been there. And as we said, I mean, we said the sigma was F over A. That's the stress. The strain is delta L over L. That's a constant. You know, so Young's modulus. We said this, yeah, we got all that, which explains this. We got this, which has already been discussed. Yeah, got all that. So if you want to find y is going to be this, which is, you know, y is simply sigma over epsilon. All right, well, that's good. This is all true. Let's keep it here because everybody's there. I'm explicitly seeing the potential variables. I'm potentially seeing everything. I'm not taking the shorthand of sigma is F over A and epsilon is delta L over L and y is equal to y. Certainly it's good to do that. It's good to know that. We should know that. But once we're here, this has got everything there like explicitly written. It's not as tidy and neat as it is where we say, yeah, sigma equals y times epsilon. Here it's F over A equals y times delta L over L. If you divide by the quantity delta L over L on each side, y is equal to F over A divided by delta L over L. Okay. Well, if that's the case, let's manipulate this. Let's multiply by delta L over L. Let's multiply by delta L over L on each side and then divide by y. And we end up getting, just giving us something to look at here. Yeah, that's a true story. If two things are equal and they're non-zero, their reciprocals are equal. So we end up getting L over delta L is equal to y over F over A. Now, is that useful or not useful? I don't know. It's maybe a horse apiece. But each, you know, this equation is born from that equation, or that equation is born from this equation. Doesn't really matter. They are derived from one another. Why am I doing this? Well, what's good about this is you can multiply by delta L on each side. You can multiply by delta L on each side, and you can get L is equal to Y delta L over the ratio F divided by A. Okay, well that's what I want to get. I mean, maybe that's why I did this whole song and dance. Certainly could have done it faster, I'm sure. But this is, in the end, this is why I'm doing this song and dance. You do it as fast as you need to do it, just know what you're doing. The bottom line is you want to find out what that L is. I want to find out what L is, given everything else that they gave me. Well, yeah, there's maybe ways around this. I'm not even hung up on the number that they gave me for the force that they were using, the 6 times 10 to the 4th. Yeah, it's good that it's there. As long as I know the forces are equal, maybe I don't even have to worry about that numeric value. I know there's going to be a stretch. There's a lot of force there, and I guess for no other reason they told us there's going to be a stretch, so we believe it. And we know there's a big force there, a big enough force that something's going to happen. Okay, good enough for me. The forces are equal. We said, I don't have any erase. There it is. F equals F. That's good enough for me. Yeah, it happens to be what? Well, 6.00 times 10 to the 4th newtons. 6 times 10 to the 4th newtons, 60,000 newtons. That's great. The big thing is they're equal. And there's something to be said here if they're equal. Okay, here we go again. And, again, the similarity of F equals Kx cannot be understated. I mean, that's big stuff there. It happens with a lot of other stuff. If you're talking about the shear modulus, if you're talking about a shear going on, or a volume is changing, there's a bulk modulus, and you're talking about volume change, or something is being sheared, and you're talking about the shear modulus, or in this case, something's being elongated or compressed, or something like that, Young's modulus. They all look like F equals Kx, and I've said that elsewhere in films. We say, wow, there's a similarity here. They look a lot alike. That I've already said. You have that. You have access to that film. Look at it. Those people that are in my class want to look at that. It's consistent with what the book is going to be telling you. Okay. So, we got all this. You got anything else you want to say? Well, yeah, I got this to say. One is twice as big as the other. I mean, I guess you could say this. The cross-sectional area of copper is 2 square centimeters, and the cross-sectional area of steel is 1 square centimeters. 2 times 1 is 2. 2 is twice as big as 1. I'm sorry, the big thing here is maybe I can get away with not worrying about the numbers too much. The cross-sectional area of the copper rod is 2 square centimeters. The cross-sectional area of the steel rod is 1 square centimeter. The cross-sectional area of copper is twice as big as the cross-sectional area of steel. If you want to call steel, let's just make it easy. Call the cross-sectional area of steel A, and the cross-sectional area of copper is going to be 2A. So that's pretty important. I mean, or at least makes it somewhat easy. I guess you could try to. You're trying to get out of an excessive amount of subscripts because sometimes you can't see the mathematics for all the subscripts that are kind of in play. So the steel is A cross-sectional area. The steel is A cross-sectional area. The copper is 2A cross-sectional area. Same kind of game being played here, guys. The L of copper, the length of the copper is, well, the length of the copper. Let's just kind of be mathematical about it. And then they just say, I'll tell you what, they got it in meters, it's 1.4 meters. The other one, the length of the steel, we're just getting the language straight. This isn't a big deal, guys, but you got to make sure you're speaking the right language. We've gone into that a little bit too. As long as the language is straight. I mean, I just looking at this, guys, A is a whole lot easier to look at than 1 square centimeter. Maybe. I know it's not a real complicated thing either. 2A is a little easier to look at than 2 square centimeters. And I don't have to worry about the units, except there's going to be cancellation. The units don't have to agree between square centimeters, square meters. That makes it easy. You can kind of throw that out the window if you're doing a comparison with similar units, with units that are the same units, with units that are the same, so to speak. So you got that. This guy, L of steel, okay, we know that. Let's see what we're going to do. The big thing is the force was the same in all circumstances. So let's see if there's something being said here that will make a little bit of sense. Let me see exactly what I want to tell you guys, what I think you need to know. Okay, you see this right here? We're going to play some games with this one. We're going to call, it depends what you want to call what, I guess. We call the steel L sub 2. We can call the copper L sub 1. Let me just see. Let me look at it carefully. Right. We can call the copper L sub 1 and see what's going on. The big thing is we worked hard to get that right there, guys. We've made some statements, some judgments here as to what's going on. Let's do a few things here. Like I said, I never like erasing any of this stuff, but let's erase what we got to erase. We've said a lot. And again, in your thought process, when you're doing a problem, you don't need to deliver a speech and run across 30 feet of a room yelling like I am, okay? Just you figure out how you want to do something and do it. The only person to whom you have to explain something when you're solving a problem that you want to just present as a final answer, the only person to whom that has to make sense is you. When you're trying to teach it or present it, when you guys in your future careers and stuff like that, that's a little different dynamic. It takes a little longer period of time to do that. But for our purposes, when we're doing this, the only person to whom this has to make sense, at least initially, and later on you can elaborate upon it as much as you want. Initially, the only person to whom it's making sense is you. I'll tell you what I'm going to do. You got this right here. Let's just say, that, first of all, this is true. Based on everything we have said, I mean, we looked at the mathematics. You saw me jump around with this and write a lot of stuff pertaining to it. If that's true, I'll tell you what I'm going to do. Let's put the original length of steel is L2. The original length of copper is L1. L2 over L1. Isn't L, ladies and gentlemen, equal to Y delta L over the quantity F over A? So that's Y sub 2 associated with steel times the change in length of the steel divided by the force being applied to it divided by its cross-sectional area. That right there is divided by, that's steel, that's copper, copper's Young's modulus, the amount of change that took place there for him, and the force that was applied going on here. Well, wait a minute. Didn't we just say some time ago that delta L1 and delta L2 are equal to just delta L? They're equal to each other. Delta L1 equals delta L2 equals delta L. These guys are equal to each other. We also said when these guys were pulling against each other, F2 and F1 were equal to each other. Delta L2 and delta L1 were equal to each other. They told us they're going to stretch the same amount. These guys are definitely different. Nobody's debating that. That's steel, that's copper. I got it. But F2 and F1 are equal. Delta L2 and delta L1 are equal. Copper has twice the area. This guy right here, copper, because we're saying that, the way we're doing it here, length of steel, length copper. Yeah, I'm going to call the steel this guy. All right, well, what's going on here? Well, we said a lot of stuff, guys. We've already said a lot of stuff. We're not going to lose a lot of sleep on it. Let's just do the job. We said that the length of the steel is capital L. So that's, okay, let's see what we got here. So that's this guy right here. So let's see where that's going to go. Length of the steel is capital L, and we really wanted to know that one. Let me go somewhere else, guys. I'm not going to have room. Okay, length of the steel, that's capital L. Steel, copper. This guy's the copper's 1.4. All right, let's get down to a little more nitty-gritty with it, I guess you could say. This was Young's modulus for the steel, which is 2 times 10 to the 11th. The amount of delta L for the steel is delta L. That's the same amount as for the copper. For the copper, for the steel. So, right. So here's for the steel, for the copper, the delta L is the same for both of those. So that's delta L here. The F that was under there was the 6 times 10 to the 4th. That's 60,000 newtons. I'll tell you what I'm going to do. I'm just going to call it F. The area of the copper, of the steel, the area of the steel, the cross-sectional area of the steel is A. For the other guy, this is 1.1 times 10 to the 11th. Also a length of delta L change. This guy's F, and this guy's 2A. Okay. What's going on here? Okay, when you do, there's a lot going on here. When you do it, a lot of ways. And again, guys, there's shortcuts here. I could have been, obviously we could be done with this 10 minutes ago, but I'm trying at least, in case we're having a problem. What do we got? We got 2 times 10 to the 11th divided by 1.1 times 10 to the 11th. Okay, so let me see, guys. Let me go. Sorry, I'm jumping all over the place here on this, guys. Just wish I don't want to erase too much of the stuff. That's where that came from. What is all this? We have here is that, all that right there. Let me go over here. Got all this. Just want to make sure it's written large enough, guys. There's a lot I'm trying to tinker with regarding the camera and everything else, the acoustics in the camera and stuff. So please forgive if it takes a little bit longer than I want it to take, but I just want to err on the side of caution on some of this stuff as well. If you deal with this, what do you got? Well, at the end of the day, you've got L over 1.4. And here we go. I mean, this is going all over the place here. You got 2 times delta L F over A. The other one, it flips. You're doing a division now, right, guys? So it goes F over 2A. 1.1 times 10 to the 11th. 1.1 times 10 to the 11th delta L on the bottom, correct. Okay, I mean 10 to the 11th and 10 to the 11th are gone. Delta L and delta L are gone. It's 1 over 1, so let me cancel them at least. You know it's a 1 over 1. 10 to the 11th, 10 to the 11th, cancel. It's 1 over 1. Delta L over delta L, that's 1 over 1. What happens here is obvious, but let's take our time a little bit. This flips, and you got this. The other one stays like this. You've got a 2, and you got a 1.1, and the rest is math. The rest is pretty easy math, you guys. Same was going on here. You just have these here, canceling, whatever. Okay. A. Kind of interesting, the 2 goes right here. You've got L over 1.4 equals 1 over 1.1. The rest is pretty simple math, guys. Right. That's it. I mean, that's basically it. L is going to equal 1.4 divided by 1.1. L is going to equal 1.273 meters. That's roughly 1.3 meters. They're given that, so just watch out. I mean, I've made it so you give the answers as accurately as possible, quote unquote. Don't worry about the significant figures and something like that, guys. But you came down to here, and you came down to here. And at the very end, you're right here. So, if they're both going to stretch the same amount, the original length of the steel had to be about 1.3, had to be a little bit shorter. If the original length of the steel was about 1.273 meters, about 1.273 meters, about 1.3 meters in length, if the steel's about 1.3 meters in length and the copper is 1.4 meters in length, when they're pulled in the manner that we've described, they will elongate the exact same amount, or at least for our purposes, close enough when we measure it. They will elongate the same amount, each one of the metals. So the steel can be almost as long as the copper and suffer the same kind of elongation the copper suffers, even though the copper, the steel and the copper are relatively close to the same length. They're not the same length, but they're relatively close to the same length. And yet when this happens, the steel, the steel does not elongate any more than the copper does, even though it has less cross-sectional area to help it out. Now, why does it hold up so well, even though it's at a disadvantage in terms of cross-sectional area? It's Young's modulus. It's Young's modulus. The Young's modulus of steel is nearly twice that of copper. So that plays a big role. It's got that tendency to want to just stay where it's at. It's not going to elongate as easily as copper does. Okay? All right. That's it, guys. Thank you for your time.